So we know how to differentiate polynomials, but polynomials, of course, are things with positive integers as powers. What happens if those powers are not positive integers? So here's a very simple one. Y equals 1 on x. Well, function x would be 1 on x. Function x plus h would be 1 on x plus h. Put it into our first principles formula. Okay, we've got an algebraic fraction on the top. Wow, it'll have a common denominator of x plus h, which I can put down in the denominator. The top becomes x minus h. And again, we get a situation where the h's can cancel. If I substitute 0 into that, I get minus 1 on x squared. Now let's look at that a little bit closer. I started with y equals 1 on x. I ended up with minus 1 on x squared. Well, hang on. If I had put that into index form, function x would have been x to the power of negative 1. And if I had just used that rule of bring down the power, lower the power, then I'd get minus x to the minus 2. Well, that is minus 1 on x squared. So in fact, this rule works not only for positive integers, it'll work for negative ones as well. The only other situation I have to be concerned with is what if it's not an integer? What if it's a fraction? But let's have a look at the square root of x. Function x is the square root of x. Function x plus h becomes the square root of x plus h. Put that into our first principles formula. Okay, somehow I've got to get rid of this h on the bottom here. So I'm going to rationalise, not the denominator like we normally see, I'm going to rationalise the numerator. And I end up with that. But what happens now is the top of the fraction becomes h, which will cancel with the h in the bottom. That's what was causing me the problem. I can now substitute in 1 on the square root of x plus the square root of x, which is 1 on 2 root x. Let's have a look at that a little bit closer. If I put that into index form, I get x to the power of a half. F dash x, bring down the power a half, lower the power, negative a half. And that is indeed 1 on 2 root x. So we can use that formula for indices which are not integers as well. Okay. So now if we get something like this, 3x plus 1 on x squared, the first thing to do is to change that into index form, so x to the negative 2, and I can apply the rule to each term. So we get 3 minus 2x to the negative 3. Now if they've asked me a question that's not in index form, then I should give my answer not in index form. So that 2x to the negative 3 I would then rewrite as 2 on x cubed. I'll just match what they've done in their question. If I have x squared root x, well that's x to the 5 on 2, because x squared times x to the half, 2 and a half, 5 on 2. Bring down the power, 5 on 2, lower the power, 3 on 2, you get 5 on 2, x root x. X to the power of 3 on 2, x to the 1 and a half, x root x. 2 on 5x plus 4 squared. Well, this is where the chain rule does become useful, because how on earth would you have expanded this out? 5x plus 4 to the negative 2. That's a bit tricky. Bring down the power. 2 times negative 2 is negative 4. Lower the power, negative 3. Diff the inside, 5. So negative 20, 5x plus 4 to the negative 3. There's our answer. If we put this in index form, how on earth would you expand that out? X squared minus 3 to the power of a half. Chain rule. Bring down the power, half. Lower the power, negative half. Diff the inside. Well, differentiate x squared minus 3, we get 2x. So I have x squared minus 3 to the minus a half. That would be the answer. Of course, a mere mortal would write down, but us super mathematicians would rewrite it like this. X on the square root of x squared minus 3. Okay, let's add this. Now that sounds better.